Let me first introduce our speaker, Dr. Nanpeng Yu. And Dr. Yu received his bachelor degree in electrical engineering from Tsinghua University in Beijing, China in 2006. And he also received his master's degree in electrical engineering and economics, as well as his PhD degree from Iowa State University in 2010. And Dr. Yu was a senior power system planner and project manager at Southern California Edison from January 2011 to July 2014. Currently, he's an associate professor of electrical and computer engineering at the University of California, Riverside. He's the director of Energy, Economics, and Environment Research Center at UC Riverside. He currently serves as the vice chair of Distribution System Operation and Planning Subcommittee of IEEE Power and Energy Society, as well as the chair for IEEE's Working Group of Data-Driven Modeling, Monitoring, and Control for Power Distribution Networks. In today's presentation, Dr. Yu will cover some key applications of machine learning in power system. And he's going to present various pure data-driven and physics-informed machine learning algorithms for power transmission and distribution systems. I hope you all find this topic interesting. All right, now please welcome Dr. Nanpeng Yu.
Thank you, Jay, for the kind introduction. And I apologize for the issues. I just saw the email at around 9:30 a.m. my time that with the link. So anyhow, so today I'd like to talk to you about some of our recent work on machine learning for smart grid. I will talk about some of the interesting applications that we developed that are based on pure data-driven algorithms and physics-informed algorithms. So this is joint work with my postdocs and PhD students, as well as previous PhD students. So we would like to also thank our research sponsors, NSF, DOE, national labs, and dozens of electric utilities, which provided the real-world data that made our research possible. So here's my presentation outline. I will first briefly talk about some of the important applications of machine learning in smart grid. Those include applications in the transmission system and electricity market, as well as applications in the distribution system and end-use customers. And then I will talk about a few key problems that our research lab has solved using pure data-driven method, which include system event detection and classification using PMU data, and deep reinforcement learning based power distribution system control. And then I'm gonna move on to the key problems that can be solved by the physics-informed machine learning methods. And these include the topology identification problem in distribution system, electricity theft detection, the distribution line parameter estimation. I'll probably skip this if there's not sufficient time. And in the end, if there's time, I will briefly talk about behind the meter solar PV generation estimation using the smart meter data. And then I will provide a few important takeaways. With the increasing penetration of sensors in power system, we can gather all of those information and started applying or developing machine learning algorithms to solve corresponding problems. The first group of problem that we could solve is in the electricity market. We all know that US have a few regional electricity markets, and we can develop price and load forecasting algorithms. We also worked on something called algorithmic trading, which leverage machine learning to solve the virtual bid trading problem from the perspective of proprietary trading companies. With the phasor measurement unit data, we can perform things like wide area monitoring. We can monitor the phase angle difference between two important power plants. We can have an algorithm that detect oscillation events. We can develop algorithms that can infer the dynamic generator parameters so that we can perform better dynamic simulations. We can do something called linear state estimation, which is extremely fast and give the operator better situational awareness. We can also perform power system equipment monitoring to identify potentially failing equipment. And finally, with the digital fault recorder information as well as the PMU data, we can develop algorithms that help us identify the location of the faults and send the crew to clear them. And then in distribution system, primarily we're working with granular smart meters. Currently, the US have much higher smart meter penetration. In certain areas, it's already 100%. So with these, we can start developing spatial temporal electric load and renewable generation forecast at the customer and transformer level. As we know, none of the US utilities currently have state estimation capability for the distribution system. However, with increasing penetration of electric vehicles and DERs, the operator really need to have better situational awareness for the distribution network. And the third application is network topology and parameter identification. For transmission system, this is not a major issue because we only have tens of thousands of nodes and lines. But for distribution system, even a regional electric utility have millions of nodes, millions of customers, and millions of lines. And it's very important for them to keep a up-to-date and accurate topology so that they can monitor and control the network. The fourth category of applications is related to customer behavior analysis. We can segment the customer into different groups so that we can send a targeted advertisement to them to maybe ask them to consider installation of solar PV system and adoption of electric vehicles. We can develop techniques such as non-intrusive load monitoring to decompose their energy consumption into the energy consumption of different components. And we can also evaluate the performance of demand response program. We can quantify how much load reduction we could expect from each of the customer when the system operator activate those resources. The next group of important applications include equipment monitoring. So traditionally in the power distribution system, because again, we have millions of smaller transformers, most of the electric utilities will leave those transformers in the field until they fail. This practice is called run to failure. However, with the increasing penetration of smart meters, we can derive synthetic measurements on the transformers and using historical transformer failure data to develop machine learning algorithms that can perform predictive maintenance. This can significantly reduce the outage time for the customers. The next group of applications that many researchers started looking at is data-driven control for power distribution system. Again, as I said, since the network model is most of the time not reliable for distribution system operators, we would like to develop something called model-free control for the distribution network. And deep reinforcement learning is obviously a very powerful choice. And in this talk, I'm going to briefly talk about some of the breakthrough in this particular field. The very last item is anomaly detection. Obviously, we still have a significant amount of electricity theft, not just in the US, but also all around the world. And especially in California, we have lots of unauthorized solar interconnection. We have very long interconnection queue. A lot of times utilities are kind of slow in approving those projects, and sometimes customers just install them themselves. And we can have algorithms that detect those activities very quickly and accurately. Okay, so now I'm going to start talking about some of the key problems that World Lab has solved with pure data-driven methods. The first one is related to the power system event detection and classification using the phasor measurement unit. So here's the motivation for this particular project. So first of all, this is a DOE-funded project. So the Department of Energy provided us petabytes of real-world phasor measurement unit data from all three interconnections in the United States, which included WEC, which is the western part of the US, and Eastern Interconnection, of course, including Newark, as well as the ERCOT grid. So these phasor measurement units data, they essentially measure voltage, they measure current, as well as the frequency. All of those measurements are time synchronized. So we know that the online event detection and classification is crucial to enhancing the reliability of power system. And if the system operator can correctly detect those events and classify them in a timely manner, then appropriate corrective control actions can be taken to potentially avoid a blackout or a brownout. So nowadays, we have about 2,000 phasor measurement units installed in the US. And with large amount of PMU data, we can now develop accurate deep learning-based power system event classification algorithms. So I will just briefly talk about some of the key methods that we used. So essentially to deal with the high dimensional phasor measurement unit input, we adopt the convolutional neural network as the base classification model. But obviously, this off-the-shelf model is not sufficient. And to make the parameter sharing scheme more effective in the convolutional neural network, we propose a graph signal processing based phasor measurement unit sorting algorithm that rearrange the ordering of PMUs in the input tensor to the CNN. Now, this is very important because in the typical image data, we have very strong spatial correlation, but if you simply randomly order the PMUs in the input tensor, you lose all those local spatial correlation. And to further improve the classification accuracy, we propose an information loading based regularization technique. And this technique can control the amount of information compression between the input layer of the deep neural network and the last header layer. So essentially, we classify the power system event classification problem, again, as a typical classification problem in machine learning. We want to classify the power system events into the line event, generator event, oscillation event, and normal operation, which means no event. And where inputs are three-dimensional tensors, the first dimension is time of the PMU measurements. The second dimension is the ID of the phasor measurement unit. And the last dimension is the measurement channel, which include real power, reactive power, voltage magnitude, and frequency. Our overall framework look like the following. We have three key modules. We take the streaming PMU data and we run it through the graph signal processing based PMU sorting that reorganize the ordering of the PMU into the convolutional neural network based classifier. And then we have a separate module that estimates the mutual information between the input layer and the last hidden layer of the neural network. And we essentially regularize the amount of information compression to produce more accurate event classification results. So again, the GSP-based PMU sorting technique tries to make the parameter sharing scheme of CNN more effective. And this technique can essentially place the highly correlated phasor measurement unit closer to each other in the input tensor. And here is the specific algorithm where we essentially obtain the Pearson correlation coefficient first between all the PMUs. And then we construct the corresponding weight matrix with these correlation coefficients and construct the graph Laplacian L. And then we do eigen decomposition of this graph Laplacian. And then finally, we can sort the PMUs according to the eigenvectors corresponding to the second smallest eigenvalue of the graph Laplacian. And if you're interested in why this algorithm guarantees that the highly correlated PMUs are placed close to each other, you can refer to our paper. We have a proof there. Here is a visualization of the spatial correlation matrix of the PMU measurements. On the left, you see a heat map with the unsorted PMUs, and on the right, you have the sorted PMUs. This is a heat map, so if the color is brighter, you have higher correlation. So you can see that after the sorting, you do have a stronger correlation for adjacent PMUs in the input tensor. Next, I want to briefly talk about this information loading-based regularization. This is actually a much more general technique that we developed to improve the performance of any deep neural network-based classifier. Essentially, you can actually develop an abstract representation of deep neural network-based classifier, where Y is the true class label, which through some physical process is generating the input data to your classifier. And then the classifier can essentially be represented by an encoder, and then the last hidden layer of any neural network that you can design could be represented by this Z. And finally, we have our estimated results, which is Y hat. So in our context, obviously X is the PMU data input, and Z is the last hidden layer of the convolutional neural network that we were designing, and Y hat is the estimated event class. So the main idea here is that we actually want to control the amount of information compression between the input layer and the last hidden layer. Obviously, with the information processing inequality, we know that we're always compressing information from input to output. But depending on how you design the network, for example, what type of width of all of the hidden layers you have, we can have different amounts of information compression. Essentially, we're trying to balance two things. We're trying to balance the effect of memorization and generalization. If you compress the information a lot, then you're really trying to better generalize. And if you do not compress at all, you're basically trying to memorize all the information that is fed to the deep neural network. And there's a right balance that we need to find between these two. And depending on the uncertainty or the amount of information that you have in the input feature space, the amount of information compression that we need is different. So on this graph on the left, we have the case where the input features have low entropy or low uncertainty. On the right, this is the case where we have high entropy scenario. On the horizontal axis, this is the amount of information compression we have from the input layer to the last hidden layer. The vertical axis is the mutual information between the input and the output. Right? In order to have high classification accuracy, we want the mutual information between the input and output on the vertical axis to be as high as possible. And the blue dashed line is the case where we have the ideal scenario where we're able to somehow learn the most optimal last hidden layer features. And that's also the case where we have infinite amount of training data to represent the true data distribution. And in this case, you actually do not need to compress information at all from horizontal axis from right to left to achieve a higher mutual information between input and output. And even with limited amount of data, which is represented by this orange curve, the amount of information compression we need is really small. However, when we work with high entropy input feature space, you can see that on this orange curve, the peak occurs at a location where we do need to compress the amount of information between the input and the last hidden layer of the neural network. And essentially, with this stochastic gradient descent optimization process, then you will be able to find a solution somewhere between the orange curve and this blue dashed line. And we want to make sure we have a higher lower bound for this trained neural network. And for this phasor measurement unit data, especially during the power system events, the entropy of the input feature is very high. So you do need a certain amount of information compression. So to implement this algorithm, we essentially need to augment the typical cross-entropy loss function with the estimated neutral information between the input layer and the last hidden layer. And obviously, it's not easy to estimate the neutral information. So we actually need to leverage the Fmine algorithm, and these are essentially additional neural networks represented by this green dash box. And this will be a separate model that will help us estimate the mutual information between the input and the last hidden layer. And we're going to be adding these to the typical cross-entropy loss function. And that's going to be our final loss function. And we're going to be using that to calculate the gradient and update the parameters of both the encoder and estimator in the classifier, as well as the parameters in the mutual information estimator. So here are some numerical study results. We're using 2 years of phasor measurement unit data from the Eastern Interconnection of the United States. We have about 1,200 labeled power system events recorded by various utilities, almost 200 PMUs in this region. We augment the data by basically sampling additional subtensors. This will be a 12-second window of phasor measurement unit data. And we create a rather balanced data set of oscillation, generator, and line event, as well as normal system operations. And here's the result on the accuracy of the algorithm for the validation data set. The red line is the baseline convolutional neural network, and the blue one is the one with graph signal processing-based sorting and information loading technique. We can see that after adding these 2 additional modules that we designed, the accuracy for the validation data is much higher. And here's the F1 score of the event classification for the testing data set for different types of events. We can see that the baseline algorithm convolutional neural network does not do a very good job at differentiating normal operation data from oscillation data. It's doing an okay job for generator and line events. But again, with the enhanced techniques that we developed, we have F1 scores that are very close to 1 for all types of system operating conditions. And also, the learned representation are actually interpretable. Here, we perform principal component analysis, a linear dimension reduction on the last hidden layer of the neural network. And again, we have these 4 different models. The top left is the most basic one, where the model struggles to differentiate oscillation events from normal system operations. And the bottom right is the most advanced model, where the hidden representations can easily separate different types of events. Again, these different colored dots represents normal operation. The orange is the line events, generator event, and oscillation. Okay. And after we finish with this task, we want to ask ourselves another question, which is, for some utilities for interconnections, they may only have a limited number of event labels. So in those cases, can they still develop a deep neural network that achieves high accuracy? We often know that with only limited data, the deep neural network won't achieve very high accuracy. So the answer that the question that we want to ask ourselves is, for example, here, can the events from the Eastern interconnection help us identify the power system events from the Western interconnection? So I just talked about the motivation for this work, where a typical neural network needs a large amount of training labels, but certain utilities or ISOs may not have a lot of event labels. And also, if you need to train a neural network from scratch each time, this is a very time and resource consuming. So we want to accelerate the training of a model for a new transmission grid by exploiting the information that we learned from a previously trained model for a different transmission. And we are able to answer the question. So essentially, the neural network that is trained to identify system events for the eastern interconnection, it does provide useful information and guidance when building the event identification engine for the western. And here we adopt the framework of transfer learning. Essentially at the top, we're doing the same classifier that I talked about earlier. After training this classifier using the data from eastern interconnection, we will be transferring the parameters in the encoder of the convolutional neural network to a new model that we're trying to train for the western interconnection. And essentially, we're only transferring the parameters of the convolutional filters within the convolutional neural network. And here are the numerical study results. The top one is the accuracy for the scenario without using the transfer learning. And different color lines represent different amount of training data. The blue one is where we only have 1/8 of the total training samples. And the right one is where we have the full training sample. The bottom graph is the result with the transfer learning. So as you can see here, that transfer learning significantly reduced the required training time to reach a desired classification accuracy. And transfer learning also helps shrink the uncertainty bounds, especially in the beginning of the training process. So here is the first problem that we solved with the pure data-driven method. And now I'm going to switch gears to talk about a different problem, which is the deep reinforcement learning-based power distribution system control. So here's the motivation. In the power system field, lots of researchers have been developing physical model-based control in power distribution system. The advantage of these physical model-based controllers is that they do provide theoretical guarantees for control performance during certain ideal scenarios. But these models rely heavily on accurate and complete distribution network model and parameters. However, in the practice, these information are often unavailable. Therefore, when people try to apply this model-based control, they often obtain unsatisfactory performance. For example, the figure on the right shows you the real-world smart meter voltage measurements for a regional electric utility. These are the per unit voltage magnitude. And normally, we want the voltage magnitude to be between 0.95 and 1.05. But on this particular circuit with very high solar PV penetration, we can see that we have prevalent overvoltage where the voltage even goes beyond 1.06 per unit. And this is a problem that many utilities observe. So therefore, with incomplete network information, we try to develop essentially reinforcement learning-based or model-free control approach. The advantage of this algorithm is that they do not need a reliable and complete distribution network model. All we need is either real-time or historical operational data, and we can use them to improve and learn the control policy. And furthermore, we can actually use them to improve the performance of an existing heuristic or human controller's control policy by further interacting with the grid. So of course, the model-free reinforcement learning-based control have their own challenges. Oftentimes, it's hard to ensure the safety of the control policies that are learned. It's easy to develop reinforcement learning-based controllers to play computer games. If you lose the game, there's no consequence. But in the real world, physical system, this is not the case. Again, for games like the game of Go, you can try to play the games millions of times, but in practice, we only have limited historical operational data from the field. So how can we improve the sample efficiency so we can actually apply this algorithm in the real world? And of course, finally, we want to ensure that our algorithms are robust It can handle unforeseen system conditions, and we want the results to be close to the global optimal solution. So next, I'm going to briefly talk about two distribution system control problems that we tackled. The first one is Vol-var control. Basically, we're trying to control the nodal voltages in the system and reduce the network losses. We also want to minimize the equipment wear and tear. So in the distribution system, conventionally, we have voltage regulating device, which are circled here. We have voltage regulators at the top of the feeders or substation. We have capacitor banks installed throughout the feeders. We also have OLTCs, unload tap changing transformers, that impacts local voltage. And these are what we call slow time scale voltage control. And we also have smart inverters installed for the solar PV systems. These could control, these devices could change their reactive power setting in close to real time. Many researchers develop a centralized and decentralized control for Vol-var control. And the second type of control problem that a lot of people look at is network reconfiguration. So the example is shown here where we have two distribution feeders represented by these two red dots, and they're serving two loads. And I have three branches here and three switches. By changing, for example, opening switch 1 here in scenario 1, opening switch 2 and closing switch 1 in scenario 2, we have different amount of losses and different voltage profile. So again, the objective of the network reconfiguration is to change the status of these switches so that we can reduce the network losses and the operating cost of the switch and minimize the loss of load, or even potentially increasing the hosting capacity of distributed energy resources. We have two types of network reconfiguration problem. We have static and dynamic. The static problem deals with the system operation condition for a single snapshot. The dynamic distribution network reconfiguration deals with the distribution network reconfiguration problem for, say, a whole day or a couple of days. Of course, for either of these problems, we need to ensure that some of the key operational constraints are always satisfied. We need to make sure that the learned control policies are safe. And these operational constraints include the voltage magnitude limit for each of the nodes in the system. And a lot of times for networks not in the metropolitan area, we need to make sure that the networks follow a tree structure. So we need to make sure that they're radial after the topology change. So here I'm showing a first piece of work where we propose some improvement to the existing deep reinforcement learning. And this is with the technique of experience augmentation. We know that the major drawback of a deep reinforcement learning algorithm is the poor sample efficiency. So the solution that we come up with is that we can generate reliable synthetic operational experience from the real-world historical operational data. So the key idea here is that we adopted the Gaussian process to learn the reward values and uncertainties associated with the operational experience. So in particular, we want to learn if I take certain hypothetical control actions, what will be the actual network loss and voltage magnitude in the system. And we not only want the point estimate, we also want the estimate of the uncertainty values. And the key idea is that we know that the deep reinforcement learning algorithm won't have very good performance if the training data is bad. So here, we essentially can discard the synthetically generated operational experience data if the uncertainty estimate for that operational experience is very high. So on this graph, we're showing the results of network loss estimation. The black dots are the ground truth network loss, with different testing week sample. And the blue curve is the results estimate from a Gaussian process. And the red curve is a deep neural network. You can see that the Gaussian process does a better job at estimating the network loss, and the results is very accurate. On the bottom left, we're showing the regression error of the Gaussian process, which is the orange curve, as well as the standard deviation estimate for the Gaussian estimates. You can see that whenever the uncertainty estimates for the network loss is very high, we also have very large regression. And that made it much easier for us to discard the unreliable synthetic operational experience. So here I'm showing some results on the testing week using a deep reinforcement learning with experience augmentation. We can see that this is the operational cost. We want these to be as low as possible. The black line is the theoretical optimal solution, which is the black line. And then the orange curve here is deep Q-learning with the data augmentation. You can see that this will be much better than the blue curve, which is just the baseline deep Q-learning. And the deep Q-learning with the synthetic data augmentation actually achieved similar performance as DQN with the true data augmentation. So that means the synthetic operational experience that we generated is very reliable. The second group of work that we did is enhancing the safety of deep reinforcement learning algorithms for critical infrastructure such as power distribution systems. So remember that the control actions learned by a reinforcement learning agent may not satisfy all of the operational constraints. So the solution we come up with is that we first formulate the distribution system control problem as a constrained Markov decision process, which is basically adding a cost function and a constraint on the cost function for the typical Markov decision process. And then we further improve the sampling efficiency of deep reinforcement learning algorithm by developing a safe and off-policy reinforcement learning algorithm. And we call this the constrained soft actor-critic algorithm. And we are essentially synergistically combining the method of multiplier with the state-of-the-art soft actor-critic algorithm, where we're not only updating the parameters within the soft actor-critic algorithm, but also updating the Lagrangian multiplier. And furthermore, we recognize that some of the controllers, such as voltage regulators, their decision or control actions are actually ordinal variables. For example, the decision variable for the voltage regulators are the turns ratios. And you can change the turns ratio, say, from 0.99 to 1.0, 1.01. And these are not just any variables, right? These are ordinal variables. We can actually adopt the ordinal network structure to encode the natural ordering between these discrete actions. And this basically improves the learning efficiency of the deep reinforcement. So here, the graph on the left shows the learning efficiency of our proposed algorithm. The vertical axis is the average weekly return. The horizontal axis on the bottom is the number of training samples for our proposed algorithm. And the horizontal axis on the upper side shows the number of samples that we need for the state-of-the-art constrained policy optimization. As you can see, we would need millions of samples to be able to learn a good control policy using CPO. But with our proposed constrained soft actor-critic algorithm, we only need thousands of samples to be able to learn a good control policy. And thousands of samples would translate to about half a year to a year of historical operation. The table on the right shows you the average weekly return and average voltage violation. These are average AVR and AVV. Again, DQN and CPO are the baseline reinforcement learning algorithm. CSAC is for proposed algorithm. And MPC is model predictive control. And MICP is mixed integer conic programming. These are optimization-based controls. As you can see, where proposed algorithm can achieve lower costs, and the voltage violation is very close to zero. And the next extension that we did in the reinforcement learning control for power distribution system is the batch constrained reinforcement learning. And the idea here is that we know that it's costly and time consuming to learn the optimal control strategy by directly interacting with the physical network. But if we are only learning from a finite historical data set that the operator gathered, this could lead to large extrapolation errors as proved by other researchers in the machine learning field. So to mitigate these large extrapolation errors, we come up with an algorithm called batch constrained self-actor grading algorithm. So the key idea here is that we want to train a control policy that not only minimize the total discounted return, but also minimize the dissimilarity between the learned control policy and the behavior policy that generated the training data. You can think of the behavior policy as the existing policy that the operator has been using to control the network. And essentially, we can guarantee that this batch constrained self-actor critic algorithm can learn a control policy that strictly improves the behavior policy that has been used to operate the distribution pool. So essentially on this graph, you're seeing some testing results on a large-scale distribution network. The green line is the batch-constrained self-actor critic algorithm. And this outperforms the baseline deep reinforcement learning algorithms such as DQN and SAC. And essentially within this framework that you're seeing on the right, the top part is the physical distribution network. It's going to be providing historical operational data. And we use a conditional generative model, CVAE, to model the behavior policy. And then we have three other deep neural networks to estimate the state value function, the action value function, as well as the control policy. And we learn the three green deep neural networks iteratively to generate the final batch constrained control policy. And the very last extension that we did in the field of distribution system control is an algorithm called consensus multi-agent reinforcement. So here, the idea is that when you have a larger number of voltage controllers in the system, it's going to be increasingly challenging to train a central reinforcement learning agent for the control problem, because the size of the action and state space will increase exponentially. So we are developing this consensus multi-agent reinforcement learning scheme where each of the voltage controller to be managed by a separate reinforcement learning agent. And each agent will learn two models. They will learn a global state value function and local policy. And the control goal is that they will try to maximize their own local reward. And to ensure that they can collaborate, we will also try to minimize the difference between the global state value functions for different agents. And this will help them cooperate with each other. And also, our algorithm is actually sample efficient and resilient against the controller or the communication system. And again, due to the limited time, I'm not presenting all the mathematics behind this. If you're interested, feel free to take a look at our recent publication on this topic. I'll just very briefly talk about some of the work that we have done for the physics-informed machine learning algorithms. The first one is the phase connectivity identification problem. So what is this problem? So basically, you have a substation, and this feeds multiple feeders. And the feeders will be connecting to the local transformers T's through different electrical wire connection. Sometimes the transformer only connects to a single phase wire, sometimes two, and sometimes three. And unfortunately, the utilities do not know exactly which phase wires connect to the transformers. But this information is critical for an array of distribution system analysis and operational tools. And researchers, including us, have developed different pure data-driven algorithms to solve this problem. For example, we can cluster the nodal smart meter voltages and differentiate the phase connections. This could achieve a pretty high accuracy in terms of detection. If you can physically measure a subset of the smart meter's phase connection, you can leverage supervised machine learning algorithms. And again, you can adopt the information loading technique that we talked about previously to further improve the accuracy. So as you can see, if you're using a baseline deep neural network, the accuracy won't be very high on identifying the actual phase connection. But if you use information loading technique, the accuracy can be boosted significantly. However, none of these have physical guarantees. Right? I know the accuracy will be very high, but it won't be feasible to achieve 100% accuracy unless you have extremely high training samples. So that's why we developed the physics-informed machine learning problem to solve the same problem. So what we do is that we develop a physical model that links the phase connection to the voltage magnitude measurements, as well as the power injections through the three-phase power flow manifold in the distribution system. And after you do this, you can rigorously formulate the phase identification problem as a maximum likelihood estimation. And this problem is actually very difficult to solve. This is a nonlinear optimization problem. You can further reformulate this as a maximum marginal likelihood estimation problem. And we can prove that that here we're showing this likelihood of observing the smart meter voltage magnitude given the phase connection and the real and reactive power measurements. We prove that the correct phase connection actually achieves the highest log likelihood value. So now with this more rigorous physics-informed machine learning algorithm, if you have 3 months of the data and with a practical smart meter measurement error, you can achieve 100% phase identification accuracy. So here's the summary of these phase identification technology. Again, if you embed more and more physical domain knowledge into the model, you can achieve higher phase identification accuracy. But obviously, the drawback of the physics-informed machine learning is that you're going to need some physical primary feeder model so that you can develop the marginal likelihood estimation method. The next key problem that we solved is the theft detection problem. So essentially, theft detection is basically reducing the electricity bill by either physically or cyberly alter the electricity consumption. This is very important because the world loses a large amount of money to electricity theft. Even North America loses somewhere between 1% to 3%. The traditional method rely on labor-intensive inspections. So we developed this physics-informed data-driven algorithm. So we found out that there actually exists some linear models between the power and voltage magnitude for each of the distribution secondaries. And all we need to do is to find a tangent plane to this power flow manifold centered at a suitable operation point. And then we can establish an exploitable relationship between the customers that are stealing power on the same secondary and the customers that are honest. Essentially, we are able to prove that the theft data will have large negative residuals, and the summation of all the residuals will be 0. So the key idea here is that we can leverage all of the individual customers' voltage data and the total secondary power consumption to accurately estimate each of the customers' power consumption. We can compare the estimated consumption and the true consumption measured by the smart meters, and these will be residuals. The large negative residuals will indicate some customers' stealing power. And this algorithm, because we're developing this with this physical model, we have very nice theoretical guarantees. So essentially, we need to develop this physics-informed method to estimate each individual customer's power consumption. And then we can measure the difference between this estimated consumption and the true consumption. And we are able to prove these 3 lemmas to show that only the customer that is stealing power will have large negative residual. And the summation of all customers' residual or power consumption estimate will be 0. So here are some numerical study results. We worked with the utility to gather data from a 12 kV circuit. We have 6 months of smart meter data from almost 1,000 customers and almost 200 transformers with synthetic theft cases. Here we're showing how accurate our power consumption estimate is. The blue curve is the actual AMI measurements. The red one is the estimated power consumption estimate. You can see the red curve and the blue curve are almost coinciding with each other. So that means we can accurately estimate the customer's power consumption just with the voltage data. We can see that if a customer K is stealing a very small amount of data of energy, then its anomaly score DK will be very high. It's going to be the highest among all 980 customers. And the second highest anomaly score is only 42. And here we're showing 4 different electricity theft scenarios. On the horizontal axis, this is the amount of stolen energy in a week, and the vertical axis is the anomaly score. As you can see, when the amount of stolen energy increased, the anomaly score of this customer also increased. And even just stealing more than 0.38 kilowatt hour of energy per hour, the customer's anomaly score will be the highest among almost 1,000 customers. And at the very end, I want to briefly talk about our work on estimation of behind-the-meter solar generation. This is very important because residential solar PV adoptions are increasing rapidly around the world. And most of the solar PV systems are installed behind the smart meters, installed by the utilities. So the utilities only see the net load data, which is the load minus solar generation. But actually knowing the exact solar PV generation is crucial to an array of system planning operations in the distribution system. And I won't go through the exact reasons for why this is important. You can look at our paper. So essentially, we are able to combine or integrate a physical solar PV parameter estimation model with a statistical load estimation model to be able to estimate the behind-meter solar generation. So we take the net load smart meter data as input, and then we first pass it through a physical model that can help us estimate the amount of solar generation and the solar PV parameters. And with the updated solar PV data, we can come up with an improved load estimate and improve the load model's parameter estimate. And after we have improved load estimate, we can subtract it from the smart meter data to come up with a better solar generation estimate and further improve the solar PV parameter. And you can do this process iteratively until a certain convergence criteria is met. And finally, we can do a post-disaggregation adjustment to make sure that the estimated generation and load is consistent with the smart meter measurement. So here, the physical solar PV parameter estimation leverages the solar PV performance model. Essentially, by knowing the size of the solar PV panel, the tilt of the solar panel, and the azimuth angle, as well as the loss of these solar PV system, we can exactly calculate the amount of solar generation. And we can use that same model to help us improve the estimate of these key solar PV system parameters. And the load model that we adopt is a hidden Markov regime model. And in a later work, we further improve this model by developing a mixed hidden Markov model to jointly model the electric load for a group of customers that are located in the same community. And this technique enables the modeling of the general load consumption behavior in all of the customers while recognizing the individual differences. And this technique allows the sharing of information across individual customers, which led to more accurate load and solar generation estimates. So you can see here, the blue is the ground truth. The top curve is for load, bottom is for the PV generation. The green curve is the mixed hidden Markov models estimate. The HMM is for previous work. And the red curve is the state-of-the-art algorithm in the field. As you can see, the green does a much better job at capturing the changes in the blue curve. Okay, so I'm going to wrap up here. So here are some important takeaways. So if you work on this field of machine learning for energy system, I always encourage you to work with the real-world data because simulation data does not possess the same property as the real-world data. And most of the algorithms developed with simulation data fail to solve the real-world problems. The second thing is it's crucial to collaborate with electric utilities and learn about their current practice and the realistic challenges that they're facing. At least from my perspective, I'm seeing hundreds of papers that are dealing with, really problems that researchers come up with, but those may not be the key challenges that needs to be addressed. And finally, we do recognize that in this field, there's a critical need to synergistically combine machine learning algorithms with the physical domain knowledge. And there's different physics that we can incorporate. For steady state operations, we can include the power flow equations. Recently, we have done work where we developed physics-based neural ordinal differential equations that can estimate the parameters of generator dynamic models. So here you need to incorporate the system dynamic equations. And similarly, you can incorporate the physical solar generation equations into your machine learning. And you can also incorporate the topology of the power network by leveraging graph signal processing techniques or physics-informed graphical learning, which I didn't have time to cover. But essentially, we're doing data analytics for sensor data that are generated from a graph. So the physics-based graph learning is also a very promising approach. We also could incorporate statistical properties of the data generated from a physical system. For example, we know, say in the transmission system, the phasor management unit data is a low-rank matrix, and we have certain sparsity patterns associated with the data. And we have different amount of entropy depending on the type of data we look at. For example, PMU has very high entropy, and the smart meter voltage data have much lower entropy. So you can design different machine learning algorithms that cater to the specific characteristics of the data set that you collect. And finally, we have unique spatial temporal correlations in different types of physical data that we gather from. We should include these when we're designing the machine learning. So I'm going to stop here. So that's it for my talk. Thank you very much for your time. So do we have any questions or comments?
Yes, thank you for your excellent presentation. And Yeah, I know that it's a very high level description of the work carried out in your group. So feel free to unmute yourself if you have any questions to ask. So actually, I do have a question about the results of the water control based on reinforcement learning. So I saw that there are some NA in model predictive control and the optimization-based control, I guess.
Right. So here.
What result? Yeah, here. Yeah, there are some NAs.
Right. So those NAs, for example, for DeepQ learning, the reason that they occur is that the DeepQ learning is not very scalable. And here, for this full-bar control problem, we're dealing with extremely large state space, which include the nodal power injections at different nodes. So the DeepQ learning actually is not capable to even find a reasonable solution to this problem. And similarly, for model predictive control, as we know, these optimization-based approach, their computation time scales exponentially with the number of controllers and the size of the system. And for this particular case, the model predictive control with a long control horizon cannot find a feasible solution to the problem within about 2 hours of computation time. So that's why those are shown as.
I see. Thanks. So is there any other question?
I have a question.
Yes,
for the part where you use the deep reinforcement learning in theft detection, do you know if this problem got reformulated in different way to address a different issue, will it work or not? So the scenario is, instead of detecting theft, can be reformulated to detect a possible spike of load, where this information can be shared in one protocol with the local suppliers, and that can be used for the next by supplier to run their auxiliary to meet the predicted spike in the load, and that can generate additional additional profit for them for that marginal or that small period of time of spike, and the risk of that also will minimize, that outage to all users. Do you think this work if it can be formulated in a different way?
So you're saying, so first of all, I'm sorry, maybe I was rushing through some of the material. So here, this is a physics-informed learning algorithm, not actually a reinforcement learning problem to identify anomaly. So I'm sorry, here we didn't use reinforcement learning for this particular application.
I understand.
Yeah. So you were saying, can you?
So what I'm trying to say, like, if you use the physical informed data method right now to detect theft, can be reformulated to detect a spike in demand, where that information can be shared with local suppliers. So instead of their auxiliary power sitting idle, that can be actually run and meet that demand locally, and they can maximize the use and basically the entire area, we're not going to have a loss of electricity due to a spike of demand or unmet demand.
I see your point. Yeah, I think that's certainly a feasible scenario. So I think that most of the time, I guess researchers formulate those as a microgrid or distribution energy dispatch and management problem that could involve, say, in your case, multiple microgrids, which may have their own on-site generation. And you can dispatch those units to reduce outage and lower operation cost. Yeah, I think that's certainly possible. Again, the challenge is that the microgrid controller and the distribution system controller needs to have better network model. And without those better models, you sort of have to also lean on maybe more data-driven control to achieve the objective we're talking about.
I see. Thank you.
Sure, you're welcome.
All right. Any other questions? Okay, if there's no more questions, so I guess we can end here. And thank you again for this excellent presentation.
Thank you for hosting.
Thank you.